Hello, everyone, and welcome back to the second video of the series AI Foundations for Developers. In the previous video, we learned what vectors are and why AI systems need them. In this video, we will understand two important ways AI represents information using numbers: dense vectors and sparse vectors. These representations directly affect how systems perform tasks like keyword search, semantic search, recommendations, and AI memory. By the end of this video, you will clearly understand why and when each type is used. Let's start with why different vector types exist. In the real world systems, different tasks require different representations. Sometimes we want exact matching. For example, finding log lines that contain the word error. The other times, we care about meaning, like searching for documents related to scaling cloud applications. Even if the exact words differ, these two needs lead to two fundamentally different vector representations. A sparse vector is a vector where most values are zero and only few dimensions have non-zero values. Imagine a vocabulary of 10,000 words. A document might only contain 10 of those words. So, the vector has 10 non-zero values and 9,990 zeros. This representation is simple, efficient for exact matching, and easy to interpret. But it has limitations. Here's a classic example of bag of words approach. Each word maps to a fixed position in the vector. If the word exists in a sentence, that position gets a value, usually 1. If it doesn't, the value is 0. Notice that word order is lost and context is ignored. The model only knows which words appear, not what they mean together. Sparse vectors power most traditional search engines. Techniques like bag of words, TF-IDF, and especially BM25 are still widely used today. If you have used Elasticsearch, OpenSearch, or search through logs, you have already benefited from sparse vectors. They are fast, reliable, and excellent for keyword-based retrieval. The biggest drawback of sparse vectors is that they don't understand meaning. Words like car and automobile are treated as completely different. Contextual words like bank become ambiguous. Sparse vectors fail when meaning matters, and this is where dense vectors come into play. A dense vector is a compact representation where most values are non-zero. Instead of thousands of dimensions, dense vectors usually have a few hundred or thousand dimensions. They are generated by neural networks and embedding models. So when people talk about embeddings, they are usually referring to dense vectors. Dense vectors looks like list of floating point numbers, but humans never read them directly. What matters is the distance between vectors. If two vectors are close, their meanings are similar. And this is what enables semantic search, recommendations, and RAG systems. Dense vectors capture meaning, not just keywords. They understand context, intent, and relationships between words. That's why phrases with similar meanings end up close together in a vector space, even if the words are different. There are many embedding models available today. The specific model doesn't matter for now. What matters is consistency. The same model must be used for indexing and querying, and vector dimensions must match. Sparse and dense vectors solve different problems. Sparse vectors are transparent and exact, Dense vectors are powerful and meaning aware. Neither is better universally. They complement each other. Modern AI systems combine sparse and dense vectors. Sparse vectors ensure keyword correctness. Dense vectors ensure semantic understanding. This combination, called hybrid search, delivers the best results in the production systems. To summarize, sparse vectors focus on exact matching, dense vectors focuses on the meaning. The modern AI systems rely on both. In the next video, we will build on this foundation and explore vector databases, starting with Milvus. Stay tuned and thanks for watching.